Title that I gave you, which was on the slide before this one, Must Laws of Nature Be Empirical? I want to argue that they need not be empirical, that there are such things as a priori laws of nature. And I want to get to the, and I want to argue that there are causal statements that are a priori true. And I want to defend this idea by looking at a particular example from science, namely the evolutionary theory, the theory of natural selection. The point I'm going to be making is not isolated to that science, but this is the example I'll talk about. So here are the topics I'll be going over today. David Hume, 18th century, great philosopher. Donald Davidson, 20th century, I guess great philosopher too, had views about causality and the a priori. I'll discuss that, and then I'll go into discussions of models of natural selection, and that'll be it. Okay, so just to make sure we all have the same understanding of the terminology that I'll be using, when I say a proposition is a priori, I mean that you can understand by reason alone whether it is true. Of course, once you understand the concepts used in that proposition, you don't have to look at observations or sense experience to decide that it's true. To say that triangles have three sides, you don't have to look at an individual triangle. If you just understand the definition of the term, the concept triangle, you can tell that it's got to be true. Related concept, analyticity, a sentence is said to be analytic means that the sentence is true just because of the meanings of the terms in it. So I think that triangles have three sides is analytic because if you look at the definitions of the terms in that sentence, you can see that the sentence has got to be true. Okay, familiar, I hope. Okay, here's what Hume said about the concept of cause and effect. One of the things he said about it that I want to focus on. I shall venture to affirm as a general proposition, which admits of no exception, that the knowledge of this relation is not in any instance attained by reasoning a priori, but arises entirely from experience. In a word, then every effect is a distinct event from its cause. It could not therefore be discovered in the cause. This is Hume's thesis. There's no argument here. He just says, this is what I think is true of causation. All statements about causation are empirical, not a priori. And here he's giving an argument for that conclusion, which I'm calling the M/E argument. That stands for metaphysics / epistemology. So the thesis is an empirical, is a thesis about epistemology that the only way to know that a causal statement is true is by sense experience. It's a posteriori, it's not a priori. And the reason that's supposed to be true, says Hume, is because if A causes B, then A and B are wholly distinct. They're completely separate events, let's say. And that's the thesis about what causation is. It's a metaphysical thesis about the nature of causation. Davidson replied and criticized Hume, and he uses the example of the sentence. It seems like a stupid sentence to consider, but you'll see why it's relevant to this question. The example he talked about is the cause of Y caused Y. And he said that's true by definition. It's an analytic statement. It's a priori. Davidson says that causation is a relationship between events in the world, and whether the relationship obtains does not depend on how the relata are described. And Hume's mistake is confusing the causal relation itself with sentences that are about causal relations. I think half of what Hume was saying was correct, what's in the yellow box here. Causation is a relationship between events, and whether the relation obtains does not depend on how the relata, the events themselves, are described. But this example doesn't work. I disagree with Davidson. I think the statement, the cause of Y caused Y, is an empirical statement because the sentence entails that Y occurred, that the event Y actually happened. And you can't tell whether that's true by reason alone. You got to look at the world and see whether, it's snowing now or the sun is shining. So the upshot is, I think the example he gives is flawed, but I think, as I'll explain, that there's good reason to think that some and here's another, let me just skip that part of it. So I think that this statements of the form X caused Y are empirical. In that I'm agreeing with Hume, whatever X and Y say, but you'll see why I think that doesn't say, well, Hume was right, let's go home. I want to distinguish three different kinds of causal claims. X actually caused Y, X actually promoted Y, X would promote Y. The first two of these entail that X actually happened, that X actually occurred, the event X happened. The third does not. That's why the statements of the first and second kind are not a priori, they're empirical. But this third kind of statement, X would promote Y, that's where I'm going to look for examples in which a causal statement is a priori true. Now, here's a would promote statement, which is obviously not a priori. Smoking would promote lung cancer. To know whether that's true, you would have to empirically investigate smokers and how often they get lung cancer, and non-smokers and how often they get lung cancer, and so on. That's all an empirical undertaking. Here's an example in the yellow box, which is drawn from a joke from Molière, 17th century French writer of comic plays, where a doctor says, I can explain why opium puts you to sleep. And the explanation is that opium has a dormitive virtue. A dormitive virtue, that's a kind of old-fashioned phrase, an antiquated phrase. It means, a dormitive virtue means something that gives the substance the power to put you to sleep. And I think this statement that I now have in the box is a priori true, that ingesting something with a dormitive virtue would promote falling asleep. It's a priori true. If something has the dormitive virtue, then of course it by definition promotes falling asleep. So this is an example of an a priori causal claim of the form X would promote Y. But it's kind of boring and uninteresting. It's trivial. I mean, it's not of any interest to science. So I don't regard that as a serious refutation of Hume's thesis. So let me summarize where we are so far. The statement X actually caused Y and the statement X actually promoted Y cannot be a priori true, but X would promote Y is sometimes a priori. Mostly it is not, but there are some examples that are. We've seen one that I say is trivial and not interesting. Let's get to something that's scientifically interesting, that has this form. And here I turn to the way scientists understand the process of evolution by natural selection. They think of natural selection as a process that occurs precisely when organisms vary in their fitness. And fitness is a dispositional property. It's the ability to do something, just like solubility is the ability to dissolve. Fitness is the ability to survive and reproduce. And dispositional predicates like solubility and fitness are defined in terms of what they would promote. If one organism is fitter than another, then you're saying that the first organism has an ability to survive and reproduce better, to survive better, to reproduce more than an organism that's less fit. So here's a very simple mathematical model of how the concept of fitness is used in evolutionary biology. You have these two traits, A and B. Every organism in the population you're thinking about either has trait A or trait B. And then you have these fitness values, of which are numbers between, in this case, between 0 and 1, and they describe the viability of those organisms. An organism that has trait A has a probability of surviving to adulthood of 80%. An organism that has trait B has a probability of surviving of 60%. And you can then ask the question, well, if the population starts with 30% and 70%, say these are juveniles or children, babies, 30% have A, 70% B, they differ in their viability. What will the frequencies be like when that generation reaches adulthood? And you might think the answer is, well, let's just multiply the percentages times the probabilities and get 24 and 42%. That's the wrong answer, because notice that 24 and 42 do not sum to 100%. Everybody in the population has trait A or trait B both before selection and after selection. So we've got to adjust those incorrect numbers of 24 and 42%. And what we do is we divide by the total there, 24 plus 42. And now we have a pair of probabilities, a pair of frequencies that sum to 100%. And what has happened here is that A has increased in frequency from 30% to something greater, and B has increased in frequency also. And that's how the model works. And let me now generalize this a little bit. We have the two traits, we have two fitnesses, they're called W1 and W2, and they represent viability, the ability to live to adulthood. We're assuming asexual reproduction and so on. And the formula here is that that's the frequency before, these are the frequencies before selection, the frequencies after, and W bar is this normalizing factor that's down here, which is the average fitness of the individuals in the population. P percentage of the individuals have W1 as their fitness, Q percentage have W2 as their fitness, so the average fitness of the organism in the population is W bar. This model is used not just in a one generation context, but you can think of a number of generations going forward as each subject to the same process. We're assuming that the traits do not differ in their ability to have, the organisms don't differ in their ability once they reach adulthood of having babies, of having offspring. So there's no fertility selection. So you can do it here. The frequency changes from P to P prime in the first generation, from P prime to P double prime in the second generation, and so on. So you have a multi-generational model of viability selection and the way it affects the frequency of a trait in the population. And what this is a consequence model. It describes the consequences of fitness differences once they exist. And you can describe the consequence model this way. You can say that in an infinite population in which selection is the only cause, and A is fitter than B, and the traits are heritable, A will increase in frequency. Perhaps a little bit more satisfactory conceptually is to talk about a large finite population, and what will happen, what this model will tell you is that A will probably increase in frequency. And of course, what's true in the model is that A's being fitter than B would promote the evolution of A, that is, the increasing frequency of A. So there's an example in which I think all three of these are a priori truths, just that they describe the model and say, if this model were true, that would promote a certain outcome. They all are would promote statements. Okay, there's a second and very important way in which biologists want to think about fitness, not just talk about the consequences of fitness differences going forward, but where do these consequences, where do these fitness differences come from in the first place? And I call that second category of modeling source models, the sources of fitness differences, which of course have to do with the way organisms are related to their environments. So here's a simple example of a source model. I put it in quotation marks because it's so simple. It's not much of a model, but it's an example to illustrate the idea. So suppose zebras run either fast or slow, and that lions prey on zebras, and lions attack slow zebras and kill them more successfully than fast ones. So a source model will say if that's proposition S were true and nothing else affects fitness, then the fast individuals will be fitter than the slow. And this expresses a source of fitness. This is an empirical claim. I mean, S is empirical, but the conditional, if S and nothing else affects fitness, then fast will be fitter than slow. That is an a priori statement. It's the conditional statement. The if statement is not an empirical statement, I say. And of course, another way to describe what what the significance of S is that S as being true would promote fast being fitter than slow. And both of these are a priori, I think. So evolutionary biologists talk about the sources of fitness differences and the consequences of fitness differences. And the arrows, I think, should be thought of as the organism-environment relation that are described would promote there being fitness differences, and the fitness differences would promote change in trait frequencies. I want to now give you a less trivial example of a consequence model that involves heterozygote superiority. So we're thinking about a pair of chromosomes, a certain location on those chromosomes, like right there, and one chromosome has either big A or little a, the other chromosome has either big A or little a. So when you put them together, there are three possible gene pairs, three genotypes that are possible: big A, big A, big A, little a, and little a, little a. And suppose that the heterozygote, that's the big A, little a individual, is fitter than the two homozygote individuals, the big A, the little a individuals are homozygotes. And we're going to assume the usual principles of Mendelian genetics, sexual reproduction, random mating. And you could ask the question, and biologists have, figured this out 100 years ago, basically. What are the consequences for evolution of heterozygote superiority? And there is a stable equilibrium. It's what happens here is not that big A goes to 100%. What happens is not that little a goes to 100% in the population. Rather, the frequencies evolve to some intermediate frequency between 0 and 100%, and it stays there. That's a stable equilibrium. And one of the elegant facts about the model is that you can calculate what that intermediate frequency is, that stable equilibrium is, just by looking at the three fitnesses. And what I have here is a way of trying to convey the algebra here in a graphical way. Good. So here is the heterozygote being fitter than the two homozygotes. And we're talking about a population that has somewhere between 0 and 100% big A. Here's the fitness of big A, and notice that it's slanting downhill, even though the three genotypic fitnesses are flat lines. Well, the reason it's going downhill is that when big A is at 100%, it's always found in heterozygote individuals. So that's the fitness of big A when big A is at 100%. When big A is very rare, its frequency is down here, and it's found almost entirely in heterozygotes. So that's why that line goes like that. And similar reasoning explains why the little a fitness line goes from this to that. When little a is extremely common, we're in a is rare. Sorry, we're in a situation in which its big A is almost at 100%. So the fitness of little a in that setting is that. When little a is very common, we're in a situation in which we're over here, and that's the fitness of little a. So that's why that line goes like that. And you'll notice, that these two lines cross. If the population starts out over here, big A will increase in frequency until it gets to there. But then it doesn't go any further because over here, little a is fitter than big A. So this is the equilibrium frequency that results in this model. There's another less trivial example, another non-trivial example of a source model, which is R.A. Fisher's model of sex ratio evolution, which I think I'll postpone. Well, I think I can do this also. Let me say it. So Darwin and intelligent design theorists before evolutionary theory existed were puzzled about why human beings at birth have a sex ratio that's not 50% male and 50% female, but like 51% male and 49% female. There's a slight male bias at birth. Intelligent design theorists thought that this was explainable by God's wanting certain outcomes to come about, which I won't describe now. That's another lecture. But Darwin and then a German biologist named Dösing, and finally R.A. Fisher in the early part of the 20th century in his 1930 book described a model of sex ratio evolution. I'll describe Fisher's version of it. So suppose the female, and by the way, Fisher's model is not just about our species, it's about any sexual reproducing species. There'll be a sex ratio, and you can ask, why is the sex ratio this rather than that? Interestingly, many species have sex ratios that are not anywhere near 50%. And one case that's been historically very interesting, both to Darwin and now, is that many social insects have female biased sex ratios. Interesting. Fisher was talking about us in mind and other sexually reproducing species. And he's saying, suppose the female in a mating pair controls the mix of sons and daughters that she produces after fertilization. And she has a resource package that she will divide between, helping the daughters to reach adulthood and helping the sons to reach adulthood. And suppose she divides that total resource package so that some proportion P is given to rearing sons and some proportion 1 minus P is given to rearing daughters. And then think of the cost of rearing a son and the cost of rearing daughters as C sub S and C sub D. And what this means is that what she'll do is she'll have a certain number of sons, which is P times T divided by the resources it takes to rear a son. And she'll have 1 minus P times T divided by C sub D. That's the number of daughters she'll have. Now, that says nothing about evolution. It doesn't say anything about which allocation of resources will be most advantageous for a female to use. But what Fisher was able to show is the interesting result that if daughters and sons are equally costly, then what should evolve is an equal investment. What will evolve is an equal investment in sons and daughters. Forget I said that sons are just as costly or as daughters. What will evolve, he was able to prove, is that this will happen. And if rearing a son is just as costly as rearing a daughter, then an even 50-50 sex ratio should evolve. But if sons are less costly than daughters, then a male bias sex ratio will evolve, where the sex ratio we're talking about is the sex ratio at birth. And what Fisher realized, as did his creationist predecessors, and Darwin realized too, is that sons are less costly. And by that, the main thing to think about is that sons die in higher frequency in the passage from birth to adulthood than daughters do. And therefore, the investment that the parent gives to them, needs to give to them, will be less to get them to that point. Some of course, survive to adulthood, but there's a chance that a son will not. That chance is greater than the chance that a daughter will fail to survive to adulthood. So anyhow, you get a male bias sex ratio if sons are less costly. And this is not obvious. It's not like the cause of A causes A. It's not like ingesting something that has a dormitive virtue will cause you to fall asleep. Boring. No, this is a scientifically interesting substantive claim, just like the claim about heterozygote superiority was a scientifically important result. So there's the boring example. Here are the two scientifically interesting ones. No, sorry, just the one on the bottom is the interesting one about heterozygote superiority. And here's the other interesting one, the Fisher equal investment model of sex ratio evolution. Here's a way to trivialize what I'm saying. So take any empirical theory T, which has the form, if IB is true, then E will be true, where IB is a description of the initial and boundary conditions you want, and just embed that conditional in this statement. If IB holds and T is true, then E is true. And of course, this last statement, this one in quotation mark here, is a priori. And you might think, well, that's all I've said you can do, and that's not interesting. I think this sort of doesn't give a proper representation of the argument I'm making here. The point is that Fisher's theory of sex ratio evolution, which is a conditional, and Newton's theory of gravitation are different from this sort of thing. Here's a way to see the example. Newton's laws of motion are empirical, and of course there is an a priori conditional where if you describe the initial and boundary conditions and add Newton's laws, you'll get a prediction. And of course the same can be done here. Fisher's model is not empirical, and you can get the if you add the initial and boundary conditions that it needs, you can get a prediction. But the point is that Newton's laws are empirical, whereas Fisher's model is not empirical. And that's a very distinctive and I think interesting philosophical fact about this and other models in evolutionary biology. So here are my conclusions. X causes Y, of course that's not a priori. But X would promote Y is sometimes a priori. It's not always a priori. Smoking would promote lung cancer is an empirical a posteriori claim. Models of natural selection often all take the form of describing what would promote what, where, course, these things about actually promoting and actually causing are empirical things. Both the would promote claims and these actually promoting claims or actually causing claims are of interest to every science, including evolutionary biology. Let me try to say something a little general in a few minutes. I've concentrated on trying to explain and maybe convince you that there are such things as a priori causal models of natural selection in science. I didn't say that yet that they are laws of nature. So what does this have to do with whether laws need to be empirical? That's the traditional view in the philosophy of science that I know about. Newton's laws of gravitation, that's an empirical claim. Well, the reason I want to call these a priori causal models laws of nature is they play exactly the same role in prediction and in explanation that empirical laws of nature play. And it seems to me that since they perform exactly the same function in explanation and prediction, we should call them laws of nature too. The fact that they're a priori does not disqualify them. Here's a second thought about the philosophical significance of there being a priori dynamical models, causal models, is that those laws are true because of mathematics. They have nothing to do with physics. So the subject of reductionism has mattered a lot to philosophers of science and to scientists too. And the reductionist thinks that all the truths of all the sciences reduce to the truths and laws in physics. Well, this is a counterexample to that. The laws I was describing, the models I was describing about the consequences of fitness differences and the sources of fitness difference, the heterozygote superiority example and the Fisher sex ratio example, they do not reduce to physics any more than 2 + 3 = 5. That statement reduces to physics. That's 2 + 3 = 5 isn't true because of physics. It's true because it's a mathematical truth. And I think that Fisher's model and the heterozygote superiority model are mathematical truths. That's why they're a priori. So this is a kind of consequence of the story I've been telling you, that you have a kind of new way of understanding why anti-reductionism is true. Thanks.